Hello everybody. It's our fourth lecture, and the idea today is to take a step back, go lower in the abstraction, and we're going to see how can we get the gates, how can we build gates from transistors. So beneath the digital abstraction that we're using, so gates are actually inside any digital abstraction. We have the real world, the continuous physical quantities, right? Because everything in the real world is continuous. But as we are using digital computers, we have to measure those continuous physical quantities in discrete values, right? So for example, examples of physical quantities: voltage on a wire. If you're measuring a voltage on a wire, that voltage has a value that's not actually discrete. It's continuous. So a position of a gear, when you assemble a gear in a shaft or in a motor, and you want to measure what's the real position of that gear, at some point you have to convert the angle that's a continuous value to a discrete value for your digital system, right? And the same in a level of a fluid in a cylinder. When you're controlling machines and on industries and stuff like that, you have to control fluid and pressure, and all these values are continuous, and you have to make them discrete for your system, right? So it's the task of the designer to choose a way to relate the continuous value that we have in nature, in the environment, to a discrete value, to get to bring that value inside the system. In our case, that we're trying to develop a computer, voltage levels will represent bits, because we're using the binary representation. In the early days of computers, in the 50s, I think, they tried to use decimal representation for the number, so you had different voltage levels for each number, but that was harder, and we're gonna see why. Because we have noise margins, right? So let's say that I have this driver. The driver is the component that is sending the message, sending the voltage, and we have a receiver. So we have output characteristics. So I read this guy, okay, if I receive something from here to this voltage here, I know this is high, so that's gonna be represented my 1, and this guy is gonna represent my 0. And between this, I don't understand, or I ignore. I have to do something when I have this value here, and I'm gonna choose when this, because it's actually not, as I said before, it's continuous. So when the voltage drops, at some point I have to choose, okay, that's already low and that's already high. So I have, or when the voltage rises again. But when I get my receiver, I have a new logic range, right? So this would be my high logic range, and this would be my low. And all this behavior, like all the differences here and the forbidden zone that I'm gonna have, it's different now, because the propagation of the signal and the errors. So all of this you have to take in consideration when you're developing ways to measure or to represent your values inside your digital systems, right? So what the designers came up with is the static discipline. So if any of my components receive a logically valid input, I have to produce a logically valid input. So if I receive this logic value here, I have to design a way to provide the same logic valid voltage, right? and but of course that is it's removed some freedom, because the range that you use for 1 or 0, they are arbitrary. You can choose and you can develop your own type of, I'm going to use 3.3 volts, I'm going to use 5 volts, I'm going to use 30 volts. But we take this freedom, and we choose the simplicity and the robustness of digital circuits. So we develop some standards, and every component, every gate has to accept a working voltage and has to produce the same working voltage. The highest, for example, the highest voltage system in the system will come from the power supply, and so of course my power supply can provide for parts of my system like 20 volts, for other parts 10 volts or 5 volts. But the power supply is going to define that part of the system. It's going to use this voltage, and it's called VDD. And so, as I said before, the choice of the VDD and the logical levels are arbitrary. So because it's arbitrary, it gave us you can group this voltage in family, in logic family. So you have components that only works with TTL, or only components that work on CMOS. And that's basically because of the logic levels that they use and they have to provide. So you cannot choose, you don't have the freedom to choose whatever logic levels that you can, but you know that any component from that family is going to work well with your design. Because of the logic levels are the same. Yeah, so the first, the Babbage, that's a historical computer. That Babbage's analytical machine was built from gears. It was able to do computations. The early electrical computers used relays and vacuum tubes, and that was expensive, that was not reliable. And modern computers use transistors because they are cheap, they are small, and they are reliable. What are transistors? Transistors are basically electrically controlled switches. So when you apply a voltage, it closes or opens a gate. It closes and the current can flow. If it opens, there's no current flowing on that switch, like a light switch. So yeah, and there are two main types of transistors that are used today: is bipolar junction transistors and the metal oxide semiconductor field effect transistors. So MOSFETs or MOS transistors. I'm gonna say MOSFETs. That's what I'm more used to. And you don't have to know all these terms and everything, but I really want the students to know how the transistors work. So it's gonna be basically so you know how a gate works, okay? So this is it's an AND gate, but you have to understand that inside that AND or NAND or OR gate, you have transistors switching. You have transistors assembled together that's switching and to make the behavior that we want from the gate. So we can ignore that low level transistor abstraction, and we can move up to the equations, to the logic, and to everything that we have to implement for our computer. There's two main types of CMOS transistors: the NMOS and the PMOS transistors. So the N channel and P channel metal oxide semiconductor, those are the types of transistors that we have. But basically what I want you to remember is that PMOS has this bubble that we put in the gate, and the NMOS doesn't have, so it's flat. And in a similar way to a switch, so we have the gate. So this gate is gonna be open or closed depending on the signal that we provide them. What they are opening and closing? They are basically opening the flux of electrons or the current here from the source to the drain. Some people call drain, some people call sorry, I forgot that there's another name, but like the drain, I think it's a better sorry, I forgot the other name, but like the drain is a good name because it's draining the power, the current in this direction, so from top to bottom. In this case it's up, but like it doesn't matter. In this, just if you have signs that indicate that this is the source and this is the drain, you can understand what the gate is supposed to do. So the gate basically controls the connection between the source and the drain. And we have voltage between 0.5, 0 to 3.3, 0 to 1.8, depending on the technology that you're using. You have to apply 5 volts here, or you have to apply 3.3 volts here for this gate to behave as the gate that you want it to behave. But what's the difference? What's the difference between NMOS and PMOS? Basically, they are opposites, right? When I apply a high voltage, I'm gonna say high voltage as a 1, for example, right? Because we're gonna start to look into more like a logic understanding of the gates and the transistors. So if I apply a high voltage here, a 1, you close it, so the current can flow from the source to the drain. If I apply 1 to the PMOS, it opens, so you don't have current here. The electrons don't flow here. So one thing that you can understand from this is that this bubble here, this circle here, is the same meaning. Let's say if you understand that one closes and let the current flow, and the opposite of it is that one opens and doesn't allow the current to flow because it's open here. So let's review. So NMOS, so you don't have the bubble here. High voltage 1, so I apply 1 here, I apply a high voltage, this guy closes and I have the signal here. If I apply 0 here, it's open and I don't have a signal. And PMOS is the opposite. So if I apply 1 here or high, I don't have a signal. I don't have flow here. If I apply 1, it closes and I have signal, I have flow here. So this is really important to understand. I think it's a good idea to review this on the notes or on the book, so you can find a way to memorize. I think the circle here is a good way because it's, let's say, it's the opposite. It's a meaning of the opposite in digital systems, so you can understand this way. But let's see how can we use those guys those transistors to build something that's useful. And we're gonna start with the CMOS inverter. That's basically a NOT gate, right? If I apply, the idea is that if I apply 1 here, if A in this case, right, it's 1, the output of Y has to be 0. And the opposite is the same. So if I apply 0 in the gate, in the input, because we have 2 gates here, right, on the transistors. But so if I apply 1 to the input, I have to get 0 here from the output. So how are we going to do that? We have the source. So this triangle, it's usually what you're going to see in the systems that represent the source or the power or the voltage. And usually it's generic because you can have different voltage. So you're gonna write here 5 volts. No, it's just like, that this is the logic levels for power that we have. And this is the most common. You're gonna see that in electronics, it's the ground. That's the word that I was trying to remember, ground, sorry. So, and this is gonna be, because we have the source from the system and the ground, and usually you have a common ground, because if that's the lowest voltage, and the same with, because sometimes you can have different powers in the same system because of different behaviors that you have, but the ground usually is the same, it's 0, right? So the inverter, how this is gonna work? We have a PMOS transistor here, and we have an NMOS here. Why we have two? Because if I apply 0 here, this guy is gonna close, and I have power here that's gonna flow to the output. So if it's 0 here, I close this guy and I have power that goes to the flow, so this is gonna be 1. And in the same at the same time, I have 0 here, I have 0 here, so this guy is opened, and I don't have the flow of this coming here to the ground, to the drain, right? So that's what's happening here. So I have 0, this guy closes, the PMOS, when it's 0 it closes, so this guy is on, this transistor is on, so it let it flow, so I have flow to my output. And in the same way, this one is off, so the power is not going to the drain. And the opposite works as well. So I have 1 here, this guy is off, so this guy is off, so I don't have current coming from the source here. But at the same time, this is an NMOS system, so this guy is gonna close, and my output, it's the same current as the ground, as the drain, so it's gonna be 0. So I'm pretty sure that I will be pretty sure that the ground, the 0, the logic 0 that I have on my system is the logic 0 that I'm gonna output here. So you can see that for a simple NOT gate, I'm gonna use 2 transistors. Again, the transistors are not like, you can see, you can have transistors for high voltage that are big, but this is gonna be nanometers in a waveform of silicon that's gonna be build your processor, right? So sometimes we have the impression that this is big, but this is really small, and that's happening in a really small scale. Let's move on to another interesting one. So that's the NOR gate. So it's the behavior of the OR, but it's the opposite. So if we have an OR gate here, it will be like 0, 1, 1, 1. But in this case, it's the NOR gate, so we have 1, 0, 0, 0. And you can see that the structure it's a little more complex than the NOT gate. We have 2 PMOS here and 2 NMOS, because we have 2 inputs, right? And we have to create a strategy here that we receive these 2 inputs and my single output, that's the result of this operation, the NOR operation. It's represents this behavior here. So for example, if I have 0 and 0, I have 2 PMOS transistors here that closes when you have 0. So if I have 0, 0, I have power from the source that's gonna flow to my output. So 0, 0, it's gonna be 1. That's what I want here on my truth table. And at the same time, I have this guy 0, 0. It's going to be open. So there's no power going directly to the drain. And so yeah, and all the other options for A and B is 0, right? So if this guy is 1, it's open, so there's no flow. So there's no flow of current here to my output. And at the same time, if this guy is 1, it's open, so there's no flow as well. So every time that this guy or this guy is open, it's gonna be 0. That's the behavior that we want. for the NOR gate. So you can see here a summary of it. So 0 0, it's 1 because this guy, the two guys are on. In this case is 0 1 1. This because of this guy that's off. PMOS transistor opens when it's 1, so it's off. And so it's 0 because we have this guy that's connected and makes sure that the current is the same of the drain of the ground, and it's gonna be 0 because of this guy here. And the same if it happens the opposite. So this guy is off, there's no power here, and we make sure that the 0 and the 0 and my output and the drain the ground has the same level, so it's 0. Of course, if you both are 1, it's off and on and on, so there's no flow again, and we make sure that 0 it's the grounded, the output is grounded. Yeah, so you can see that for example, for the NOT gate, we only need 2 transistors to represent that. For the NOR gate, we need 4 transistors already. So you can see that as more transistors allow more complexity. You can develop more complex gates if you have more transistors. But after you have the basic gates, we can we can go one step up, and we just work with implement the equations, the Boolean algebra, and the logic behavior that we want for our system. So after we have the basic gates built on top of the transistors, we can work with the gates, and you can see that here we're gonna have like several transistors for each one, and on top of those transistors that we have the gates, and putting those gates together, that we're gonna have our equations and our behavior that we want. And yeah, so that's what I want to talk today with you. Thank you. See you in the next class.